So my name is, give me 1 second. So my name is Dr. Akhan Almagambetov, and I'm in the EC Department of SEDS. So I was asked to talk about some of my new research directions, and I'll talk about those today. One of the new research directions that I'm working on is in the field of industrial automation, or SCADA. Before that, I used to work with computer vision. I still do some of that research, but it's not my main focus anymore. And some of my prior research was related to FPGAs and some low-level mathematical operations, which were optimized for FPGAs. Before Nazarbayev University, I worked at Embry-Riddle for about 6 years as an associate professor, and there was most of my research in computer vision. So let's start. Most of you are probably aware of SCADA systems in some way, shape, or form in some capacity. So those things are pretty much everywhere. They're used in oil fields. They're used in, for example, wastewater management, power management, and even manufacturing. So back in the day when they were first invented, not many people thought about their security because these are from the 70s. And this kind of mindset trailed through up to the 2000s. And that's where all the problems started because they're very easy to attack. And even proprietary systems where the protocols are hidden and things like that, they're pretty easy to break once somebody either socially engineers something or things like that. So now people are obviously increasingly more aware of the security aspect, but there are a lot of problems associated with bringing security to SCADA. So we'll talk about those today. Now, there are, I guess, 4 iterations of SCADA systems. So we started with monolithic, or what's called classical SCADA. This was back in the 70s and 80s, where you have some what are called remote terminal units, and they're connected to some hardware. Now those in monolithic SCADA, those remote terminal units were directly connected to what's called a master terminal unit, which was basically giving all of the instructions to the remote units. And it was, if data needed to be retrieved, let's say it's from a pressure gauge or something like that, so that could have been done. Obviously, this type of implementation was only useful within a confined space. So for example, if you're trying to manufacture something that's perfect, because you don't really need to go over the internet as much, even for like small wastewater management facilities, that's okay. But when you get out into the larger field, you need something networked, because usually like for a power grid or something like that, that system can span a lot of distance. So next came distributed SCADA, which was basically kind of like a networked infrastructure where you had the MTU, and then through the network, the RTUs were connected to the MTU. Back in the day, in the 80s and 90s, this was through modems or some wireless connection, like radio or something like that. But it still was not fully networked because most of those protocols were fairly closed source. And basically the distance, you couldn't go over a very, very big distance. So next came what's called modern SCADA, or networked SCADA, and this type of SCADA system works over the internet. So all of the components are basically connected, interconnected through the internet. And this is where all the problems come in, because obviously all of these things are accessible. If you don't implement the firewalls correctly, or for example, an intrusion detection system correctly, then anybody pretty much can have access to that system. So that's what I'll talk about today. And we'll talk about some attack vectors that exist and things like that. So infrastructure 4.0 is something that's being developed. And it's basically just an upgrade of the networked SCADA infrastructure. but right now, not a lot of places are implementing it, or the standards have not been set because basically people are trying to get over the hurdle of trying to upgrade from monolithic or distributed SCADA to something networked. Alrighty, so let's see. The attack vectors on current systems, there are many. So you basically can infiltrate a system fairly easily for a modern hacker. So the biggest threat is basically physical security and access controls. So passwords and things like that being accessible to the outside, as well as public information. Typically, disgruntled employees leak this information, or hackers socially engineer their way into a company and they obtain this information. There's also a lot of stuff that's running from back in the day. So all the legacy software from like the classical SCADA infrastructure, nobody can swap it out because that would basically cost a lot of money and resources. So in a lot of places, you still have the old systems from the 80s basically running everything, and they're trying to integrate them into the new infrastructure. So that comes with, upgrade restrictions. Obviously, some things cannot be upgraded. Wireless is not as much of a problem anymore, but still, there are some open wireless access points, and wireless is being used for SCADA. So that presents some problems as well. And then there are also OS vulnerabilities. So hackers try to exploit, even though it's a real-time operating system running on those programmable logic controllers, there are still zero-day exploits which hackers can use. But mostly the infiltration comes from either physical security, because now the SCADA system is spread out so far that people cannot manage it. And then basically just access controls, passwords, things like that, and remote access. That's probably the number one issue. So if we look at the most recent attacks from, let's say 2000 onward, then unauthorized remote access is probably the number one reason. Well, it's not probably, but it's the number one reason why certain systems fail. The next is malware. And then comes physical security and denial of service. So denial of service is actually pretty big, because if you wanted to, oops, go back. If you wanted to, you can basically just spam those units in the field because they are connected to the internet with some bogus requests. They might reject all of them, but still the influx of those requests is too overwhelming for the system to deal with them. So basically, that system kind of goes down. But unauthorized remote access still is the number one reason why systems are hacked, and that's what we're trying to address with our research. So you all saw the networked SCADA infrastructure in the first slide. So basically, I have a master terminal unit which communicates with your remote terminal units that are actually connected to hardware. And there's some geographical separation in most cases between these. These RTUs are connected to some hardware that they control or that they interact with, like valves and gauges and things like that. And then through the internet or some communication equipment, we get back to the master terminal unit, which basically gives them instructions on what to do. This data can be stored in a database. Typically, like there are logs that are dumped, and then the operator can interact with the master terminal unit and kind of oversee the operations. The new architecture will actually kind of break control away from just a single unit. And it's fully backwards compatible, which is, I guess, the number one reason why we're pursuing this. Not a lot of companies want to invest into new infrastructure. And basically, each RTU, which is connected to some hardware, is separated into two parts. So there's a virtual logic unit, and there's also a hardware logic unit. So those are two separate programmable logic controllers. And they can be the same exact model that was there prior. We're just adding an additional PLC to the mix. So each RTU will also have an intrusion detection system that's just off the shelf. So things like that can be purchased and installed right by the unit. And typically they have that already in some way, shape, or form. And the hardware logic unit is the only unit that's connected to the actual hardware that you're controlling. So be it a valve or something else, the virtual logic unit never sees hardware. And basically, both of these units are physically co-located, and they're hardwired together. So under normal operating conditions, the master terminal unit will basically send instructions over the internet to the virtual logic unit.
Sorry, Professor, can I ask something? I'm sorry.
Yep. Go ahead.
I just have a quick question out there. I registered for this event. Why I didn't get my registration link right after my registration when I asked, and I needed to wait until, so I came late a little bit to this event.
Sorry,
I'm not asking you, Professor, but I'm asking the people who are in the club.
Sorry,
Is this some kind of discrimination or what? Why should I send an email if it should be sent already when I registered? Could you please clarify? Thank you.
Sorry, this was not a discrimination and everything is okay, just maybe problems with mail sending. So, Professor, sorry for interruption. You can
I
continue.
didn't even notice it. I was seeing that you were online.
Sorry.
And you sent it. It was not.
But
it's not justification at all.
Perhaps you could figure that out after the presentation. I'm sorry.
Yes,
but,
yes, Diana, can you stop, please? Since it's not a matter
I
of
can go
meeting.
through the presentation, and then you guys can figure this out. Okay. So basically, let's see, where was I? Okay, so we have the virtual logic unit, and we have the hardware logic unit. Those are co-located. They're in the same location. They are the
Excuse me, Professor, are you talking right now?
I think no, I think Professor Sakham have some problem with internet. So let's wait, maybe he will fix it.
I'm sorry, Professor, that I interrupted, but it was really a point that I needed to make it right away.
We are sorry that you didn't get. Okay, so you can continue sharing the screen.
Okay, give me 1 second. All righty. Oops.
Yes, we can see it now.
Okay, perfect. Good. So the reason why the IDS is connected to the hardware logic unit is because basically the hacker, for example, can intercept the communication between an MTU and the virtual logic unit, or basically what they think is an RTU, and they can send it some bogus instructions. So a couple of attacks that happened in the past relied on that. So the hacker was able to intercept the communications and then maybe like hammer the valves to bring them out of service, or turn up the pressure in the pipeline to make it explode or something like that. So the IDS is designed to not I guess, intercept bad traffic, but to intercept traffic that will signal to the hardware logic unit to perform something that's out of the ordinary. And the way this works is that over the course of some time, let's say a month or so, all of the operations that are happening are being logged to some kind of a database, which the IDS has access to. Once the IDS detects that something is going on that's out of the ordinary, it severs the connection between the virtual logic unit and the hardware logic unit. So now the hardware logic unit is kind of functioning on its own. And to the hacker, what happens from the point of view of the virtual logic unit is he's still getting back responses that may seem correct. So for example, if the hacker says, well, turn up the pressure in the pipeline, then the virtual logic unit will reply, okay, the pressure's up, and then it will send corresponding data. So typically the hacker is only able to infiltrate individual nodes in the system. So they will basically think that they've infiltrated the whole entire system and they're controlling it, when in fact, the connection has been already severed. Now, because all of the hardware logic units will be connected to a local network amongst each other, as soon as that connection is severed, this hardware logic unit will let others in the network know that they've been compromised. And then the communication can happen through some other units in the system that also talk to the MTU, let's say. And an arbiter will basically decide whether or not to accept that instruction. And the way this is going to work is that as soon as this thing is compromised, then at random, 2 additional units are assigned that can talk to the master terminal unit that can relay the instructions. And it basically comes to a vote. So between these 3, do they all agree? If 2 out of the 3 agree, let's suppose, then the instruction proceeds. So for example, if it's an instruction to turn down the pressure and all 3 units agree, even though they're not really talking to the hacker, only one of them is, then this instruction is valid. It can go through. Now, probably the biggest thing here is that this is backwards compatible. So a lot of companies will be interested in this because they don't want to revamp the entire infrastructure. They've had enough problems kind of revamping it when they moved from like classical SCADA or distributed SCADA to a network SCADA system. So they don't want to put any more resources into this. And as part of the research, we're building something called SCADAville, which is basically a simulated real world environment that includes a couple of water tanks, valves. So there are pressure sensors, valves, there are pumps and things like that. And basically this thing is supposed to emulate a water distribution system within a city on a very small scale. So all of the testing will be done on this system. So I've recently applied for a grant, which I'm just waiting to get it approved. I think it's about $200,000 over 2 years. And it's to build the system, to test the software, and maybe improve some of it. So that's basically the gist of my current research. Like I said, I had some research in computer vision. If you're interested in that, we can certainly talk about that. You can send me an email, or I do also FPGA research as well. So if you have any questions right now, I guess I can answer them about this current branch of research.
So please, students, you can write your questions in the chat and we will read them and answer.
Professor, what kind of language do you use when you work with FPGA?
So I typically use VHDL just because I'm used to it. But in the past, like when I was in graduate school, I used Verilog. But right now it's mostly FPGA, or right now it's mostly VHDL. So another question is, what is your computer vision research about? So mostly it was for traffic, so traffic detection, counting, and things like that. That was in my PhD program. I've also, once I wrapped that up, that was under 2 grants. And once those were wrapped up, I went on to more aerospace fields because Embry-Riddle, where I taught before, was an aerospace engineering school mostly. So there we had a wind tunnel where you could basically visualize low-speed airflow. If you were to put like a model of an airplane in there or a model of a wing or something like that, then you were able to generate like smoke streams that you could visualize. Now, whenever we do that, it's very challenging to kind of quantify those things. So obviously the researcher takes a picture, and somebody that's very well versed in the field, they kind of look at the picture and they say, well, this is good. But there's no way to mathematically, I guess, quantify the performance in the actual wind tunnel. So my computer vision research was about capturing those smoke streams, and they're actually really cool. Like if you Google them, just Google smoke stream wind tunnel, you'll find some really cool videos. And basically, out of those videos, I had to extract some data as basically data points, see how continuous those smoke streams were, whether they were turbulent or laminar, and based on that, generate some kind of a numerical answer, whether that I could assign to a design. So let's see, another question is, are there any strict requirements for students who want to participate in your research? So no strict requirements really, just if you've taken a class with me, that would be awesome because I know you. If not, then no problem. I currently have a master's student working with me on this research. And but other than that, no, just, and you can do that to any professor. You can just walk up to them, strike up a conversation, and maybe they'll invite you to their research team. So, yep. Anything else? You're welcome. What would you suggest to students who are struggling in deciding the topic for their research? Talk to your professors. That's probably the number one thing that I would do, because I can tell you from my undergraduate days, the first 3 years, I basically did not really participate in anything because I was too shy to talk to professors. And only in my senior year, I started doing research. And as an undergraduate, I think it's very, very hard to either settle on a research topic or just pick it out. I mean, even if you know what you want, it's very, very hard to kind of put that into like a research framework. So faculty that have been working on research for a while already, first, they know all those problems that you're facing. And 2, they already have some really, really cool, I guess, problems for you to solve. So if you're interested in something, I would suggest first looking at the school website, and under every professor, it kind of lists the research that they're doing and what they're interested in. And based on that, just pick a couple of professors, talk to them. Hey, what kind of research are you doing? Here's my resume. Make sure to send your resume because otherwise, I can't connect the face to what you've done. And then basically you can go from there. Some professors might not be interested. Some professors will. So my suggestion is to contact a few professors and talk to them about your research. And hopefully in the spring we'll be completely in person. And then you can just walk up into a professor's office and say, hey, I'm interested in your research. And then you guys can talk. So that's the absolute best way to do that. Let's see. So do you accept first-year undergraduate students? Depends. So when I was working at Embry-Riddle, I had a undergraduate student that I accepted right at the end of her first year. And she actually worked with me for all of her 4 years of college. We made a patent together. and we were very, very productive. So it depends on how well prepared you are and how willing to work you are. So yes, I guess that's the answer. So where can we read more deeply about your SCADA or computer vision research? Let's see, that's a tough question. So some of the articles have been published, SCADA has not, because it's something new for me. I've been only working on this for about a year and a half. So hopefully in the future you can read up on it, and after my grant gets approved, I can send you the grant application if you're interested. So just email me. But for now, there isn't anything concrete on paper. What kind of background should students have to work with professors? You have to be hardworking and you have to be interested in the topic. I guess that's the only background. Obviously, some skills that the professor is using in their research would help, like if they're into programming or something like that, then knowledge of that language would be great. But most of the time, like for example, the student that I worked with from her first year, she didn't know anything when she came in. She actually, in high school, she did not even prepare for the major. She was a computer engineer, and but she was willing to work really, really hard. So that alone basically is all you need to be driven, I guess, in research, and be interested, obviously, in the topic.
Okay, so thank you for your presentation. And now it's time for our second speaker.
Thanks. I will stop the sharing, and thank you for inviting me.
Thank you. Okay, now it will be our second speaker is Professor Mehdi Bagheri. Professor, are you here?
Yes, I'm not sure whether I connected or not. Can you see me? Okay, hello.
Yes, we can hear.
Hello, everyone. I'm really happy actually to see you, ladies and gentlemen. Thank you very much, Professor Akhan. I just joined 2 minutes before and I've seen that he was talking actually very useful information, very productive information actually, how you need to conduct the research, how you can join 2 different teams. And basically all these information are quite important. Of course, we are happy here to support and to help as much as we can. Anyway, very good to see you. So let's get back actually to the presentation to save the time. I was thinking that it's afternoon time. It's evening time almost. So basically I was thinking that to provide more photos and type for you rather than to have too many actually, you know, passages. The host, am I allowed to share the screen?
Yes, you are allowed to share, so we can start.
Okay, thank you very much. Can you see that? I hope you can see that. Yeah.
Yes,
Any
we
feedback?
can see.
Okay, fantastic. So thank you very much from the IEEE session members that they provide this opportunity to talk with our student. We really wish that the number of the events in this form, you know, basically getting increase and we can communicate with our actually NU students so very, very closely. Well, more or less, some of you have already worked with me and some of you are new student, but I wanted to tell you that I'm working on energy, power, and control system. So to be more specific to talk about actually our field, which I really hope that it would be interesting for you. From the name, it's completely clear that we support group of energy, which we are talking about actually generation of energy and management of the energy, of course. We cover and we talk about the power system, which of course, when we talk about the power system, we talk about specifically on the electricity. We talk about the control system, automation system, smart systems, basically industry 4.0, IoT application for the controlling different kind of system. And I want to say, yeah, we are working from system point of view, because when we talk about the energy, power, and control, we can talk about actually just simple programming, or sometimes we can talk about programming and in the meantime, implementation over the system. So when we talk about our research group, then I'm saying our research group, so we are few professors which we are working on energy, power, and control systems. We are talking about the systems. What does it mean, system? So system means that we need to go for implementation and practical work. So it is true that, for example, if we develop something with the Python language, or if we develop something, so basically with the machine learning or AI or any other technique, so it will not remain as a kind of program. We will implement it over system, and we have got different kind of example, which from NU we actually, more or less support, the entire industry. But let's go ahead and a little bit talk about the detail of the research, which we are doing in this specific group. So in our research area, I'm saying our research area because not only me, but there are some other faculty members, they are working actually in this field as well. And we have very close collaboration, so basically together. In terms of the research area, I can say that we are working on power system operation and restructuring. What does it mean, this one? This one means that in the new format of the electricity generation and transmission, we have the market of the electricity. It means that as the electricity generator or perhaps power plant, you are coming to the market, you will give a bid, and you will give, oh, this is my offer, this is actually the price of my electricity. And if there is a customer, he would be happy actually to buy from you, or perhaps he will reject you and he will go and buy from another power plant. They call it restructuring. So Kazakhstan, many countries in the world, from the conventional electricity dispatch, they move basically to the newest structure, which is the market of the electricity. And from the conventional price of the electricity, they moved actually to the dynamic price. Dynamic price means that the price of the electricity would be based on the demand. If the demand is getting increased, of course, in that case, basically the price would be increased as well. If the demand decreases, of course, the price would be decreased. Anyway, that's the field which we call it restructuring. Many parts of the world, they have a significant market, I can tell you, and just, they even finished that and it is completely under operation. From 2018, after our discussion with the KEGOG, we realized that KEGOG is planned actually, to move forward for the restructuring, and they right now working on this specific case to open the market for the electricity generation, transmission, and distribution for basically, Kazakhstan, because Kazakhstan is a very big country. From the north, it's connected to the Russia, and from south part, it's connected to Uzbekistan, and the other, of course, country. And there is a significant potential for marketing of the electricity. We generate the electricity here, and we sell it actually to the neighbors. Anyway, to make the long scenario short, the other project, I will explain some of the project for you. Then I will get back and I will tell you that in which project we have opportunity for the RA position or for research for. The second project, which very significantly we are working on that, that's a smart meter for the grid and of course for energy efficiency. So that's something that we have a product, that's a specific unique product in all over the world. I'll show actually this product to you. And that's talking about actually the smart management of the entire grid and management for energy efficiency and implementation. We work over right now maritime high voltage equipment. What does it mean, maritime high voltage equipment? At the last slide, I will show you that there is a specific proportion, energy system for each and every ship under the ship. And for the entire actual compartment, we have a research project and we are working on that. So we are working on renewable energy and its application. Of course, everyone knows that that's quite something crucial these days. And implementation of renewable energy, either it's going to be actually solar energy, wind energy, photovoltaic energy, geothermal energy, tidal energy, all of these things. So basically are quite significant, and Kazakhstan are supposed to have significant amount of renewable energy generation by 2030 and more than that by 2050. According to the Paris Agreement. So more or less, you're familiar with the renewable energy. I don't need to explain about that much. So we are working on railway electrification system. One of the significant problem in Kazakhstan is the icing phenomena. Icing means that, so the ice, when the snow is collected over the wire, after sometimes when the wind is actually, blowing, so it will turn to become ice, and it's going to be really hard to remove those ice from the electrification system of the railway, and in the meantime from the power lines. But it is very crucial for the electrification system, because when the train moving forward, there is a pantograph and there is a catenary, and that actually pantograph is touching those ice, and there is a problem. For example, we have got a report that during the winter time, if one single train comes from Almaty to Astana, then they have to change the pantograph. Of course, they cannot turn off the system to de-ice the ice which is collected over the wires. Therefore, they are looking for a kind of a real-time technique, how they can melt the ice using the energy circulation and short circuit in the meantime when the system is in operation. So this is another actually, practical project which we are working. More or less the project which I'm telling you, all of them are practical. So harmonic and mitigation technique is another actually, project which we are working. Green electricity generation, including distributed energy systems and microgrid. To explain about this case a little bit for you, I have to tell you that previously, last years, we have got actually energy from the generation side is transmitted actually to the distribution side. So one side is generator, the other side is consumer. But these days, with the concept of the microgrid, we have already generation from the customer side, from the consumer side as well. For example, if you have a specific yard, or if you have a specific building, or if you have a cottage in the remote area, you can put your wind energy system over there, wind turbine over there, and you inject the electricity actually to the grid, and the company, Kegoid, will pay money to you because of the renewable energy generation. You will put a meter, and you will get money for that. Anyway, so this will call it basically green electricity generation and distributed energy resources. We work significantly on condition monitoring and prognosis system, a smart city and electricity consumption. That's another thing. I'll introduce one project in a smart city for you. Transformer and cable test techniques. That's another field which we are working, and we have a team members on this case. As I told you, icing and de-icing system for electrification system, and basically, for power lines, power electronics and energy conversion, and high voltage insulation monitoring and substation. For example, in terms of the last project, we have a specific project using the image processing and machine learning. We are able to send UAV to capture different photos from the insulator in the power lines. We analyze those photos in the real-time condition, and then we will tell you that whether there is some, we can classify actually, the quality of operation of those, insulator. Previously, they had to shut down the electrification system. I mean, the power lines, they send the people over there, and the people, still they are doing the same, but I'm saying that, so basically that's a project which is under process right now. Let's talk about those projects which we have potential for the RA position. However, if you are fitting to each and every RA position, it depends to your background a little bit. Because, for example, 2 weeks before, I've received some message, from the high school people that they are really interested to work, for example, on dynamic wireless charging of electric vehicle or the other project. But still, we need to wait for those people from the high school. They again, they get to the university, they pass electrical circuit theory control system. Couple of courses they have to pass to be able to join to our team. But anyway, looking to the project, number one is the dynamic wireless charging of electric vehicle. This is one of those projects which we have a few team members. So in this project, and basically we implemented this technology, and I'm really proud to say that Nazarbayev University and our team is one of those just few teams which they implemented dynamic wireless charging but for electric vehicle. What does that one mean? By the way, the setup was in C4 building, but right now we moved the setup actually, to the 5th floor to our laboratory because they wanted to do something on the 1st floor of the C4. That's why we moved the entire things, over the 5th floor. But anyway, getting back to the project, this is quite famous project in the world. And that one means that basically we plan, and we did that. We plan in this specific project to charge the electric vehicle when you are driving actually, over the road. So for example, we will add a kind of new road or new lane actually to the other lanes of the road. And then over that specific road, if your car is equipped with wireless charging system, it would be able to actually grab energy from actually, electric load. How are we going to make an electric load? We would have transmitter and receiver coil. So basically for the road, and in the meantime for your car. For example, BMW 8, some of the, full option of the BMW 8, I think they have basically wireless coils. For those cars which they have a wireless coils, of course, they are able to grab this energy. let me tell you that this project implemented successfully. There are a couple of videos over the YouTube. You just go to the YouTube, search my name, and after that, after my name, you just put EV, electric vehicle. You will see different videos, which I don't know, different medias they collected and they recorded last year from this project. But this is a project which more or less right now we are still working on that, because we're going to go for basically larger scale. The other project which right now we are accepting team member for that is actually dynamic domino wireless charging of UAV using the power lines. But more or less everyone knows that one of the significant problem. So in basically UAVs is their battery energy storage system. After 30 minutes, 20 minutes, they're going to be dead. So and of course they have to get back to the station, operator change the battery, and again they get back to the operation, which doesn't make sense, of course. So it is true that for movie making or for actually media, they are using this sort of the drone. But if we're really going to use this drone very effectively, we have to provide wireless charging. So without landing and without getting back actually to the station, these UAVs are supposed to be charging this project. However, how we can charge it? So that's going to be a big deal. Are we going to send something over there to charge these UAVs? No. The solution is actually using the electromagnetic wave around actually the conductor of the overhead lines. So it's quite a significant project. I'm telling you that there are lots of interested companies that how we can actually grab this energy, that energy which is right now is wasting. So basically in the environment, we're going to grab that energy and convert it to electricity and charge the energy storage battery system. So this project, we have, I think, 6 or 7 members, but based on your background and your interest, we are accepting actually more team members from the bachelor, master, and of course, PhD student. This is another project which we are working. So basically on that, and we have to finish this project, hopefully within next two years or 2.5 years, and we come up with the pilot. When I'm saying pilot, it means laboratory scale implementation. That's our plan to perform. The other project, which in this short time I can present for you, is a smart monitoring system for energy consumption and for building and of course for the transformers. What is this guy talking about? So this project is talking about actually energy management. So it means that over this project, so we should be able, at the end of the project, we should be able to detect what kind of device is right now connected actually to the network. And based on that, we would be able to manage your device. What does it mean? It means that when we come to the dynamic tariff, and the price of the electricity is going to be actually, basically very significant, because that's a dynamic tariff. It's not a conventional tariff. In conventional tariff, everyone knows that we have 2 prices. One price is actually for the daytime, and the other price is for the peak time of electricity consumption. But when we come to the dynamic tariff, so you will see that sometimes in some hours the price would be significantly increased. Instead of to be, for example, 15 tenge, it would be 60 tenge. Of course, if the price is 16 tenge, you don't want to actually run your dishwasher or your washing machine. So you're going to run it whenever. So the price is quite actually low, because you're going to save money. You don't have to pay 4 times more actually for electricity bill, or even 10 times more. I can tell you that we have got a case back in Australia, so that the price was 10 times larger. So because there was a fault in the system, there was lack of the electricity in that time, and because of the market, a huge amount of the demand, the price, dynamic price, rised up actually to 10,000 larger. So a smart monitoring system is a kind of intelligence system which can detect what kind of equipment is connected actually, to the network. When I'm saying to the network, I mean to your building, to your apartment, and then it would be able to manage your equipment. Recognizing the signal of your equipment, it would be managed. For example, if you turn on actually the dishwasher, it wouldn't be work. So it will wait until the tariff gets down during the, I don't know, maybe midnight, and then it will start working. For example, it's possible actually that you give some of your preferences or option as well. For example, washing machine cannot be started during the midtime, but some other equipment, they can work actually, during the midtime. But anyway, that's a smart monitoring system for the smart building, which we are working on that. We are working on IoT-based smart meter. So, and I'm happy to tell you that 3 versions of this smart meter already implemented practically at Nazarbayev University. And that meter will provide you this opportunity to manage the entire the equipment and entire the appliances in your home, in your industry, in your office, using actually your application. So in the meantime, it is able to tell you that and to advise you that how much would be your electricity consumption for tomorrow. Therefore, it's quite significant. So basically, and it can provide reactive power, active power. There are some detail of this project. So we have different version already for this equipment. One of them is actually alpha version, which we developed this one. You see, it is more simple. So in 2018, this version has been developed in 2019, and this is actually the version in 2020. And I'm happy to tell you that all of them, as you can find actually in this picture, tested in industry. I mean, they are calibrated and they are working. So all of the project which we are working, more or less, it would be terminated to the industry. In terms of the smart city, sorry, I'm going very fast because I don't have that much time. They have given just 30 minutes. In terms of the smart city, we are working on real-time air pollution detection system using artificial intelligence. I have a commercialization grant right now. We have open position in this actually, basically system, which we're gonna to detect and forecast the air pollution using the artificial intelligence and actually, pollution actually, distribution, monitoring. We're gonna to develop a device. That device would be implemented over the bus station for each and every bus station. And we collect the entire information from different bus stations. And then we have an application which can tell you that in real time, how much is the pollution in some part of the city. Therefore, if you have a heart problem, if you have an asthma, or if you have children, the application can simply able to tell you that whether this part of the city is a suitable place for actually breathing for you, or you have to leave this part of the city. It would be able to give you the warning, all the information, and all of the things. So we have a team right now, 6 people are working in a commercialization project. So with me on this specific case, and we developed the first setup, the electronic transmitter system, and of course the application, initial application. But this is one of those projects which is demanded with the country. I remember that I think it was 2 years before that we have got some bushfire. I remember not a bushfire, it was a fire. So basically in Almaty, and it was creating a kind of a smell, and some people became panicked. So if this system was available over there, so the people could exactly monitor where is the source of actually, that fire, and they can actually, manage, their stress. Continue our discussion. We have another project, and that one is the renewable energy for moving train. That's another project which we have got initial actually study over this project, but we haven't started still this project. This is one of those projects which is really interest of European people because they don't have enough generation, and American people, of course, and of course Eurasia, because we have a huge amount of railway system. And basically we plan to go for this project. We discussed with the KTG. They show initial interest so for this specific case. So one of the subsidiaries company of the KTG, and this is one of those projects which we're going to go for that. We believe that using actual renewable energy over the train, we would be able to produce, or I can tell you that to reduce at least 10 to 15% of the energy consumption of this train, specifically when the train is in the station. So that's another project. But let me tell you something. Train itself, it has a auto generator as well. I mean, when it is moving forward, there are some electro generators so under these actually wheels, and they are generating electricity for some of the trains as well. So there is a big discussion on this case. So we are working on a smart grid and microgrid, as I told you. So, and a smart grid and microgrid means that we have to move forward to have zero energy building, hopefully by 2030, or if it is not realistic, by 2040 or 2050. Zero energy building means that we need to be able to manage the entire grid, entire actually, city in a form to be able not to provide any single kilowatt hour energy for buildings. Buildings should be able to generate their own electricity themselves and then consume. This is ideal case. I'm not sure when we're going to reach to that, but we are working on a smart city in that case. To have such a kind of system, all the neighbors using the transactive energy management, they have to communicate together. For example, you will generate electricity, and that management system will recognize that two neighbors, the other side, two of your neighbors, the other side of the road, they need this electricity, and you will transfer that electricity over there. Sometimes you need electricity, they will transfer to you. All of these management systems would be operated on smart grid and microgrid. And basically, the electricity generation here, I mean, by the power plant, conventional power plant, they are supposed to go for the electric vehicle charging. Or we can touch vice versa. We are giving the conventional actually generation to the grid, to the buildings, but we use actually the energy which is generated in your building for your electric vehicle. One more thing which I wanted to tell you, in future, you will see that you would be able to discharge your electric vehicle over the grid and get money actually for that electricity which we are giving to the grid as well. They call it G2V and V2G, which, you know, that's a big discussion. So the other project is energy electrification system for railway and marine application. So this is another project. Looking actually to the ship. So we usually find the ship from this point, I mean, onwards to the top side, because the rest of that is under the water, yes? But if you go under the water, there is a big generation, transmission, and distribution system. So from this side, generation, transmission, and distribution system to give it to the propeller of the ship. The entire system is actually, you know, power system and control, of course. So including electric motors, inverters, you know, switch gear, and all of these things, which we are actually, you know, working on those things on different aspects, which if you are interested, I can explain to you. In terms of actually railway system, so I have to tell you that we are working on high-speed train, and specifically maglev train, which they are working, and they have roughly 600 actually kilometer per hour speed. And basically that's totally electromagnetic, and that's totally high voltage coils under actually the train, which we changing the pole of those actually, you know, poles, you know, basically north, south, this train can move forward. And how frequent you can change with your inverter, actually this south and north pole, it can adjust, so basically the speed of the train. So that's another case which we are working. These projects, which I told you, these are more or less active projects. So that we have team members actually for this project. So let me tell you something. You know, we use all the codings, I don't know, Python, AI, machine learning, as a kind of mathematical tool for implementation and support industry. Therefore, these are our mathematical tools. For example, if you know the programming language, let's see C++ or Python. So basically, you would be able to develop actually the technique. So do we have a project that we don't know Python or programming? Yes, of course. So we have got different projects which they don't need actually to have the programming language. But last year, I'm proud to tell you that basically we implemented the project for the European people, and that was totally management of the energy systems in Sweden, Germany, and Portugal, using actually artificial intelligence with the combination of the power system management. Anyway, these are some of those undergrad courses which they are related more or less to our research area, starting from the power system analysis, renewable energy, power transmission, high voltage energy generation, up to some postgraduate actually, you know, level basically study. So in our team from 6 years ago, so basically we have had 51 bachelor students, which they work in a project, graduated, 28 MSc students, 3 PhD students, and we have 7 active members right now, 5 MSc from the BSc, 5 from MSc, 3 from PhD, and we have 2 postdoc, which currently they are working on this project. We have grants, we have actually, you know, position available for those people which they are interested, and they have to have, you know, some background about those things which I've explained. About the laboratory, well, our laboratory is quite famous in Eurasia. So some of you, maybe you have visited our laboratory, but if you haven't visited our laboratory, I advise you actually, you know, to search it in the Google, in the YouTube, so it would be pop up. You can look at actually the equipment. But whatever we have here, it's quite unique in our laboratory in all over the world. For example, this device, which is CPC-100, so that's the only device for entire Eurasia, or I can say at least Kazakhstan. I'm not sure about Uzbekistan, you know, Turkmenistan, you know, Tajik, and actually the other countries in the Eurasia. But you know, whatever we talk, we practice it. So I mean, practically. In terms of our industrial collaboration, all the names which you can find here, more or less, we have had a collaboration with them. So some of them, like as a SAP, you know, probably what is the SAP? SAP is maybe one of the largest programming company in all over the Europe. So in Germany, they have an office here. So for SAP, for the last 2 years, we have done a project. So we have had a project actually, you know, basically with Alagil. We have had a project, you know, all of these signs which you can find here, we have a discussion. For example, recently we have got a request from the industry of Kazakhstan to design charging station for the electric vehicle, because we have got the discussion, the number of electric vehicles, specifically Tesla car, step-by-step getting increased. And you know that Tesla car consume huge amount of the electricity. For example, to charge the Tesla, you need to have, you know, let's say a 20 kilowatt, you know, power station, I mean, electrification station, which not simple, actually, you know, charger can do that. So therefore, you know, we have to design a new charger for those sort of, you know, basically vehicles. Number of Tesla, number of BMWs, and those electric vehicles getting a step-by-step increase in Kazakhstan. Specifically, we have number of them based on our report in Almaty. So this is more or less basically presentation. It seems that I'm hopefully on time. So each and every project has got lots of detail, but well, sorry, IEEE members, because I have had very short time and I had to, you know, pass it very fast. If there is a question, I'm happy to answer it. If not, I'm happy actually to listen to the chair lady.
So, dear students, you can write your questions in the chat. And thank you for your presentation. It was very interesting.
Thank you very much. You know, when there is no question, my student knows that. When there is no question, it means that either the presenter was very good or the people were very sleepy. So anyway, joking. So one gentleman asked, yeah, that's
Can I
why.
ask a question?
Yeah, sure.
Thank
So
you
my
very much
email
for
address, sorry. Before you're actually, you know, asking your question. So basically, let me share my email address. By the way, it's available over the website of the university, but here you go. Yes, sorry, man. Yes, you go ahead.
I want to ask about your research of dynamic recharge of drones. It quite impressed me, but I thought, what about economic prospects? How, for example, you're going to recharge your drone from the power lines, but how much do you think people owning that sort of drone should pay for that power? Because it's kind of would be like, you know, robbery if you just take that energy.
Very fantastic question. So I'm telling you, very, very good question. I didn't have enough time to open discussion. Okay, let me tell you. So over the power lines, we have two types of the signal. One type is electromagnetic signal, which, like as a circle, it is turning around actually, you know, the wires. And the other one is the electric field signal, which two wires in opposite direction, they are forcing each other and there is electric field between these two wires. Those electromagnetic signal, which they are around the wires, they would be dissipated automatically because of the Lenz's law and Faraday law. You know it from the physics, yes? And basically, if the operator, let's say Kagok, not touching anything, they cannot do anything. It's like as a corona. Corona is a kind of phenomena. By the way, our corona is before that corona, I mean, before medical corona. We are the first people with the corona. So corona is a kind of phenomena which, due to the high voltage signal, you will ionize, the line would be ionized automatically, the oxygen around actually, you know, the wires, and it will create a kind of hissing signal, something like as a zzz. You heard it when you are passing under the power lines. That corona is out of our hands. We can control it, we can reduce it, we can do many things. But if corona happens, so that's wasting of the energy. That electromagnetic signal, according to the Faraday law, it would be over there. Either we grab it or we are not grabbing. Therefore, if we are putting a kind of system over there, which we call it receiver system, close to the power lines, we don't want to touch power lines. We never touch power line. UAV will just approach the power line. It will get close to the power line. If we are able to grab that electromagnetic signal which is in the space, so in the air, and then change that electromagnetic signal, convert it to the electricity, then we are lucky. Yes. So therefore, we are not consuming or we are not supposed to overloading the line. Therefore, we are not, supposed to pay for that. However, I mean, it's not a robbery. However, I believe to your question completely that there should be a permission from the government side, that the government knows that we're gonna to grab this energy. But let me tell you a little bit background about this, because this project, I initiated this project because I was thinking that these UAVs, if they are able to get a charge from the power lines, they can be used in the police force. You can put one UAV over each and every street. It's flying over that street, going to the north, coming to the south, and it's monitoring the entire street. And when it is finished, when the battery is finished, it gets back actually close to the power lines. Power lines are everywhere in the city. That's distribution line. Get close to that one, get charged, and recharge itself and get back actually to the main station. Since it is supposed to support the police force, even if we consume electricity, government would be happy to pay for that. But generally speaking, we are not, consuming any electricity. And to be more specific, a little bit more technical, so each UAV, big UAV, I mean drone, has 60 watt-hour typically battery, which is almost nothing. I mean, you can charge it with 2 ampere. It's just a matter of the fast charging system. So 2 ampere as compared to 2000 ampere over the lines is totally ignorable, because that 2 ampere can be even a loss. But thank you very much for that question. So we will inform government for sure.
Thank you very much.
You're welcome. But very, very good question. I mean, you have a concern about that. Well, let me tell you something. This robbery is very important in smart meter development. When we wanted to start the smart meter, for 1 year, we were just studying what are the technical ways to grab the electricity. I mean, robbering the electricity. There are many solutions how you can actually bypass the lines, unfortunately. And basically how you can bypass the smart meter. There are many techniques. All of those thief guys, they are professional, but we have to be more professional than them. So there is no more way. It's like as a, I know it's overtime, but it's like as a cheating, A professor, they are trying actually, right now to develop different technology to stop the cheating. But those people which they are cheating, they are professional. They always, day by day, they are finding different ways, which we don't know about that. So technology, is under progress. Well, there is a question. Thank you very much. Yes, that's a very good question. We have got a team members from the second year, which those team members which they are from the second year, we will start from literature review for the literature review with them. Yes, in your class, I didn't mention in the number of the BSc student, but we have 2 team members from the second year right now. We have more team members from the third year, and we have more team members from fourth year, of course. But yes, we will start with those people from literature review. Even it is better, because you can get training from the beginning, and you would be able actually, to be dominant over the topic. You just communicate with me, so I will answer it, and then depends to your project, I will refer you to the team members. You're welcome. Any other question? I think yes, please. I think the time is over. Sorry, I don't know who is the next presenter. Maybe Professor Hashmi, but basically, yes. If there is one more question, I'm happy to answer.
Okay, we can continue because.
Oh, we can continue. Okay, so let's go.
Oh, cool. I have a question related to the dynamic wireless charging of electric vehicles. As I know, due to the large air gaps, there is a leakage inductance of the air core transformer. and this could lead to the low coupling coefficient, which is very, it could lead to the low efficiency. I know that you can place capacitors in a parallel or series configuration so that you can increase the efficiency, but how did you solve this problem? I'm just curious about.
Okay, that's very good. Guys, it's very interesting question. That's why I'm gonna get back because we have enough time. So you know what the gentleman's saying? Thank you very much for this question. The gentleman saying that here, you see, if I can get back to here. Yes. Gentleman saying that here, between these are transmitter coil under the electric rod. Yes. Here there is a receiver coil. We have two problems here. One of them is the air gap here. That's the air gap, vertical air gap. But the other one is actually, if you look at these coils, these are our laboratories, by the way. So this is our lab as well. I mean, well, you see, we simulated this coil at first with the ANSYS, and then we fabricated the same coil. You see, this is our lab. Anyway, a gentleman saying not only this one. In the meantime, he's saying that there is a big gap here because of the core. So that's the air core, and the, you know, basically coupling between receiver coil and transmitter coil, it would be affected. The question is completely right. So basically, we will address this problem with increasing the frequency. Since you increase, if you look at the formula, if you look at actually, you know, to the coupling equation, if you increase the frequency, then you would be able to manage the coupling. This is one thing. The other things, you know, when this coil is moving forward from this transmitter coil, it will get a huge amount of the charge. But when it's coming to this gap, I'm not sure whether you can see my cursor or not, but I really hope you can see that. So when it's coming actually to this gap between transmitter 1 and transmitter 2, it would be actually a kind of drop. They called it pulsation. These two actually cases can be, you know, addressed with increasing the frequency for the coupling, and the other one with playing with this gap. How much should be actually, you know, the optimum size of this, you know, gap? That is something which is really significant. We have got lots of publication on that. You know, even Ainur Rahimbai, she was my student. I mean, she was working on this project. You know probably Ainur from TA, you know, category. I mean, she's TA. She published a paper talking about the optimum distance between these two coils. So, you know, therefore, coupling is always significant problem. Not only coupling. Somebody maybe claim that, oh, there are some passengers here. Yes, we have few passengers here. If you're going to increase actually the signal here, I mean the flux, then there is a possibility that you get infected. You don't want to be infected in the electromagnetic signal, for example, for 30 minutes. So how we can control that one? In the meantime, we get charged for this car. So that there is a solution for that. So we have to be very careful about that one. In the meantime, if we're going to get a proper charge for this car, the system, there would be a system, not now, in future, it would be able to tell you that when you come over this lane, you have to drive with maximum, let's say 60 kilometer, 50 kilometer to get the maximum charge. If you go faster because of the lack of the time, because of less coupling, as you mentioned, you will get actually charged in a longer time. I mean, all of these factors, yes, exactly, should be taken into consideration. However, we can address that coupling with shape of the coil, with frequency, and, you know, or we can change, you know, the transmitter coil from the segmented shape. It's a segmented coil, 1, 2, 3, segment. We can make it to a continuous coil. You know, if you have a continuous coil under the ground, so some people offer that one, then the problem of the coupling would be fixed. The pulsation would be fixed, and we can just play with the frequency. But the main answer to overcome is frequency. So we will go sometimes up to 80 kilohertz. However, our setup, which we implemented at C4, it's working with 20 kilohertz because our MOSFETs, they are getting huge amount of, I mean, they would be really become hot, and this heat should be transferred to the environment because it needs cooling system. So basically, we cannot go further than 20 kilohertz. When we go for 20 kilohertz, some of our MOSFET would be burned. So we are working on this, you know, a specific case. Hope I have answered your question.
Yes, okay, thank you.
There is a question about AC to DC and DC to AC converter. You see, you see, what's the reason that you have to have AC to DC and DC to AC? Because you're going to keep control over the frequency, yes? So in the first AC signal which you generate, you don't have control over the frequency. Let's say you will generate a signal with 25 kilohertz, 25 hertz, sorry. But you're going to have a signal with 50 kilohertz. How are you going to change this one to this? You need to make it DC, and using that DC, again, you make it another AC. They call it DC to AC, AC to DC. When you have a DC to AC to DC, DC to AC, then you have a keep control over the frequency, because frequency of the final signal relate to the switching of your IGBTs and MOSFETs. Yeah, any other question? Yeah, thank you very much. Thank you very much for your time in the evening time. You're welcome, everyone welcome. Let's have close communication, basically, and we can work together. For those students which are second-year student, we can start to work together, but when they become third-year student and they pass electric machinery and power system analysis, then they would be able to go for technical part and simulation. There are some simulation study which that should be done in fourth year or even in master. Therefore, we have to look at actually, to the year of a study, and based on the year of a study, we are giving the task. For example, let me tell you something. Those people which they are working right now with us for the second year, and they are second year BSc, they are fabricating the coil and they are working with the frequency conversion. So that's their task right now. For the fourth year student, they are working on something else. Master student working on something else. Yeah. Okay, thank you very much that you put your time to listen to me. Any further question?
Because we are still waiting for the next speaker, our next professor, so that's why we can continue to discuss. And if you have some questions, you're welcome to ask.
Rustem is asking, in which city you're going to make your air pollution? Well, it's a very good question. Probably Nur Sultan. But some of the team members, they offered us some cities in the east part of Kazakhstan or in Almaty. But frankly speaking, because our station, our main office is here, we prefer to have Nur Sultan. By the way, before we go for the city measurement, we plan to implement it inside the campus. I asked already team members after the development of the transmitter systems. Those systems which they are grabbing, the different, components, CO2, CO, all of these components. So they are putting those actually equipment in different places, and then we program everything so to see whether we are able to grab the signal from every point, and then we increase actually, the distance, and we move these devices to different parts of the city. These devices are supposed so basically to be installed with the discussion of Akimat, hopefully over the bus station, because bus stations are spread everywhere. So, and basically we can give the code number to each and every bus station to monitor that device. Therefore, we know exactly which device is damaged and it needs to be fixed because we have the code number of that device in that bus station. About the electricity, for the source of the electricity for this transmitter, we can use the electricity in the bus station, or we are working to use renewable energy. But because of the winter time, maybe we have to use electricity over the bus station, because winter here, if we have snow, somebody has to clean actually those solar panels. There's small solar panels over actually the bus station. But that means that we have to pay money, but we don't want to pay money. So that's why we can simply use actually the electricity in the bus station. But in some of the city in the world, like as Dubai, for example, like as Abu Dhabi, in Dubai, so we can use renewable energy to feed actually these transmitter coils, these devices which they are collecting actually, you know, signals. Yes, Ust-Kamenogorsk is going to be a, you know, city which can be tested. Yes, agree. There are some, okay. Temirtau might be, these are all of the city which you guys mentioned that can be tested. Well, let me tell you something. We will develop technology here. Right now, we develop a technology and we are waiting. We patent it. It's already patented. A couple of our technology. We have 2-3 patents. Right now, there is an interest from industry to do the investment. When industry comes to us and they're going to do the investment, we will say that this is a technology and this is a prototype. Here you go. We will sell this technology to you. They will take it. They will test it in different places and they will get back to us. For example, say that this is a problem. Then we will fix that problem. They'll say that this is another problem. We will fix that problem. Because you guys, when you make something as a kind of, you know, support service or after sales service, you still need to work and address different bugs and different problems. I don't know how many of you are using, for example, Apple phones. Yes. Apple, I have some, at the moment which I'm talking with you, I have some friend over there, for example. They are working on just debugging the mobile of the Apple still, and that should go forever. So that's the same for a project. You see, we will make, for example, you know, some device, but it will take a time that we practice it for different cities. We get the feedback, improve it, alpha version, beta version, gamma version, lambda version, delta version. So, and then step by step, we improve actually that device. And that's something that should be practiced in different cities. And that would be happen for the entire project. It doesn't matter, it's a power electronic project. It doesn't matter, it's the AI project. For the AI project, which we implemented for the Sweden and Germany, they are writing back to us that, for example, we need these to be added, that to be added, that should be deleted. So, and still we are just, you know, working on that. And then we provide another version of that project and we again actually, you know, update. Yes, there, it just usually. So there is a question about the drone. Yes, that's a good question. The question, I think it's talking about how we're going to grab AC signal. However, UAV has a battery, and battery is a DC signal. We have a rectifier. So you see, we have different stages. One stage is we are grabbing electromagnetic energy, we convert it to the electricity. The other stage, using domino wireless power transfer, we use actually the high voltage insulator. We will install different coils under the high voltage insulators. We bring this actually, you know, energy up to reach it to the top of the tower, because UAV cannot go and get very close to the you know, wire. So because of the corona has 300 megahertz signal. It can disturb the telecommunication signal radio frequency of controlling system of UAV. That's why we have to get a little bit far away from the line. And the best place is actually getting close to the arm of the line, because over there, everything is grounded, everything is earthed. The tower is earthed. And then using domino, we have to bring this signal up. Therefore, we have to increase the frequency. When we reach to the top of the, insulators, and we reach to the arm of tower, then over there, we would have a rectifier to rectify the signal, or we can put rectifier over the UAV. So, because it is a 60 watt-hour battery, it's something like as this, you know. The inverter is something like as this. It's quite a small circuit. So we can simply actually, you know, it doesn't actually influence the payload and just, you know, mechanical load of the UAV. It's a simple circuit. We'll put a rectifier, rectify the signal. We'll give it actually for, battery. The problem is not this part. The problem is that battery should be fast to grab the energy. That's the case. The other part, we will work on that and we will implement it. But with the Institute of the Battery, with chemical engineering, we are working actually how we can have a fast battery. yeah, that's the case, which needs huge discussion.
Okay, sorry, we had a little confusion with the schedule. So now Professor Hashmi connected.
Yeah.
Now up next is Hashmi. Thank you, Professor Mehdi.
Yeah, thank you very much, guys. Thank you, all the attendees, and thank you very much, IEEE actually members. I'm giving the floor to Professor Hashmi. Mohammed, yes, please, you go ahead. Thank you, guys. Have a good day. Bye.
Thank you. Professor Hashmi.
Sorry, guys. Actually, there was somehow it was my fault that I could not see the time properly. But anyway, so I'm here. I won't take long. So I just wanted to apprise you about the circuits and system research that we do at Nazarbayev University, and actually more than this thing, it's just to show you the career path in this very, very interesting domain. Okay, so can you guys see this?
Yes, we can.
Okay, so some of you know me, many of you do not know me. So just to tell you that I am Mohammad Hashmi, and I am a faculty member at SETS in Department of Electrical and Computer Engineering. You can reach me through email at mohammad.hashmi@nu.edu.kz or in my office that is in 3rd block 3E.534, or mostly you will find me in my lab in C4-224.1. So we do a lot of things in circuits and systems research at Nazarbayev University. So I would like to just make you aware. Many of the students work with me, and to show you that these interesting things really lead you to somewhere once you are really successful. So before I move on, circuits and systems is actually a very, very broad theme. If you see this applications areas of this circuits and systems, that's the big umbrella. Actually, if you talk about consumer electronics, you talk about television, mobile phones, tablets, computing, you talk any. So that is at your device level thing, like you have some stuffs, gadgets. Then we talk about a system-centric aspect, that is Internet of Things. So actually it is really Internet of everything. Whatever device you have, if it is capable of connecting to wide variety of devices, that falls under this umbrella of Internet of everything, not just Internet of Things. And along with that, Internet of Things in itself is useless if we talk, unless and until we have two very strong capabilities. One, the storing capability, another is communicating compatibility, and that is provided through cloud computing platform. Then within circuits and systems, we also do a lot of things about neural networks, artificial intelligence, machine learning, and there are many new things that always keeps on coming. Then we also do a little bit of bioelectronics. That is actually the spine for electronic health, digital health. That has been talked by various governments around the globe. But so far, due to paucity of cost-effective technologies, it is not really in matured state. So lots of people, lots of groups worldwide, they work also on bioelectronics, and that also falls under the umbrella of circuits and systems. Then Professor Mehdi Bagheri was talking about UAV. UAV is actually incomplete without circuits and systems. If you do not have communication capability, you do not have computing platform to do many data analytics, if you do not have, say, for example, even within communication between each other, like with sensors in UAV, then you do not have that UAV is useless actually without circuits and systems. Otherwise, it will be just a mechanical box. Then let's get to more like consumer usefulness. We talk about RFIDs, automotives, everybody has, you see, cars, automotive electronics, you have sensors. So everything has this circuits and systems component. You name anything and everything in this wide technology domain, you will find the space for circuits and systems. So if somebody is working in this category, in this domain, then they will find variety of opportunities in different segments. It depends again on the interest of individuals. But if you have interest in circuits and systems, then you are in a very good place. It has lots of applications, lots of job opportunities. And eventually that's what we do. If suppose you are spending time on bachelor's degree, master's degree, doctoral degree, you have certain aspirations to be successful in your professional career. And within electrical and computer engineering, circuits and systems is one of the major domains. So let's move on, like what we do in our group. So if I have to define the broad directions, then definitely it falls within 5G and 6G, that is upcoming, both are upcoming actually, connections and devices. So I do also like devices and circuits for communicating each other, and device modeling and device development for facilitating that communication. So it is called 5G, 6G connections and devices. If I show you a broad spectrum where our works fall, then you name IoTs, autonomous vehicles, AR, VR experience, laptops, computing, wearables, data centers, utilities and infrastructure, whether it is a smart grid and those things, or even smart homes, medical electronics. So everywhere, our little bit we are trying to contribute. And of course, it is humongous, and it is physically or realistically impossible for one human being like me to do all this. I rely on my top class talented students who work on these things. I am just trying to mentor and guide. And now if I have to focus on this broad thing, so what exactly we do? So what are the specific research areas? Then if I have to name few, I just noted down like 5G and 6G communication circuits, advanced antenna techniques, wireless information and power transfer techniques, wireless body area network, IoT security and trust, RFID and IoT seamless integration. So in the past decade, like 10 years, one way or the other, I have touched upon, or my group has touched upon some of these segments. Let's see briefly, like in 5G, 6G communication circuits, what is happening? Actually, what is that? In theory, it doesn't look like what is this 5G and 6G communication circuits? So if we have to talk about that, so let's see. We have cell phone. Within that cell phone, if we do not have this transceiver component, see for example this, it will be just a mechanical and plastic box. So if you rupture apart any old phone, you will see there is a very tiny transceiver circuit. And that transceiver circuit has many integrated circuits, integrated chips. So this transceiver is having a plethora, a number of ICs. So, and if we divide our work within this segment, so we do contribute in 6 different directions. We do circuit design, we do device modeling, as others in world over they do. Then we also do measurement techniques. Since once we design these circuits, it's also important to develop some mechanism to measure them, since there are no standard ways to measure. It's actually, they are all evolving at a rapid pace. Then we do system validation. Say, for example, we developed some components, we combined together, and we try to validate whether whatever we wanted to achieve, are we getting that? So we try to combine them and try to see if really our efforts are making sense. Then we also fabricate circuits. We do then some integration scenarios as well. Say, for example, we develop some circuit, we develop its model, and then nowadays, those of you who have slight ideas of LTSPICE and those type of simulators, they are low-end simulators. But for these high-end designs, we have to use high-end EDA tools, we call. So within that EDA, we have library components, libraries, packages. So in integration, that's what we do. We develop these circuits, circuit models, then we integrate in the EDA platform to make it useful for wide range of communities like across the world. So they are all open source. Say, for example, in circuit design, what do? We do various types of circuits, like we design circuits, really we design circuits in our lab, or we do some layout stuffs. So this is for some component for multi-frequency circuits. This is for some example for switch. So we developed some switch for high-speed 5G circuits. Then we also do modeling. Modeling can be done using machine learning, equivalent circuit. There are a variety of things. So this is just one depiction of neural network multi-layer model. But this is just a depiction, but like device and circuit models can be done differently in different like various styles. Then we also do this measurements techniques and system validation. So we have real instruments, stuffs we measure, and then we try to validate. Say, for example, how do we validate those systems? By looking at the current and voltages, and we then anticipate, did we really want this? Or it is anomalous. So by looking at current and voltages, we try to analyze that, okay, yes, these are like, they are really mimicking the behavior that we expect from our circuits and systems. Then we also do this fabrication in our labs. You can see these different types of circuits, planar circuits, and various techniques we have in our laboratories supported by engineering workshop here. So we try to do that and then validate in our lab. And then, as I mentioned, we do some integration type work as well. So we suppose out of all these stages, we develop based on data, we develop models, and then we make it useful in wide range of circuit design by making libraries of those models, and we incorporate them in EDA tools through that, like ADS or Cadence, and then of course lots of programming is needed in that in Python and MATLAB. But again, it is like students are much aware about those programming things nowadays. But essentially, that's what we do in our group. In advanced antenna techniques, you see nowadays you go anywhere, even on internet or anywhere, you will see 5G, a small cell, and a small cell Wi-Fi and all, and you will see these, signals going out. But what are those? They are antenna actually. Without antenna, those all depictions are redundant. And if you go further, even in United States, I was just looking at some of them. There are, even lampposts, they are being used for antennas for signal communication, 5G antenna. You can see different companies, AT&T, Verizon, Sprint, T-Mobile, and there are many. So those antenna techniques, they are developing antennas for 5G and 6G. So about a first question that can come, what is happening with existing antenna techniques? Actually, they are not really useful and effective for 5G and 6G centric communications. Why? You see, the idea is, of course, antenna is a key element, but they should be extremely efficient. But the existing antenna techniques, which are available in literature, they are useful for frequency ranges and data rates that conform to 4G applications at most. Even their sizes are big. And now we are talking about 5G, we need miniature. You see, these are the antenna things. Antenna is a key element. Antenna should be efficient. Antenna should be miniature. Antenna should be adaptive. Since in 5G, you have a variety of frequencies and your antenna should be adaptive to them automatically on the fly. And antenna should be omnidirectional. It is easier said than done. So So these are the requirements of 5G stuffs. So, and normally variety of techniques are utilized. You have meta surfaces, you have SMA, you have patch, you have prototype development, and then their measurement and characterization inside anechoic chamber. And what is anechoic chamber? That is actually vibration free and actually a vacuum type environment where when we measure the antenna, it is really free from anything. It is just antenna behavior. And we have in our lab that facility that we do. Moving forward, one of the buzzword nowadays is wireless power transfer. Especially you see wireless charging happening around the world, especially in big cities like London, Singapore, Tokyo. They have charging stations. And they say wireless power transfer. But believe me, even with all those successes, and they are at lower frequencies anyway, they are still not mature. They are maturing, even at those high power levels. And at higher frequencies where you have mobile phone techniques and all, these are still in infancy. And that is only wireless power transfer I'm telling. But if you want to have wireless information and power transfer, where you just do not transfer power, you also transfer information as well. And they are really required in applications that is, you see, in wireless body area network, for example, where doctors, they want to monitor the patient's health. So it's called digital health, electronic health. In those things, just that, say, for example, I give you a scenario where some patient has pacemaker antennas. And earlier it used to be, okay, first battery based. So every 7 years they used to operate and put another battery system. After that, wireless power transfer came. And now the idea is to, and no, after, even before that, there was rechargeable batteries that were placed, and then you had this wireless power transfer. So you charged them. But the problem was existing technique is very high power and they burn the flesh of the patients. So they are not really mature. So lots of efforts are being done, especially this work is a hot cake in Japan. They are putting a lot of effort. So that is there. But then the doctors thought, and even the electronic health they require, that why only power, like powering the battery and this? How about maintaining and monitoring the health, like of the heart, for example? For that, you need information transfer as well. So heart should keep sending information to some data centers. And how will you do that? When you have wireless information and power transfer. And that is still in infancy. And wireless information and power transfer for biomedical applications, that is still elusive. Success has not been, it's only prototype that is in development, but in real applications, they are still in infancy, they are elusive. And why it is so difficult? You see, the key features in a WIPT, they must be miniature. Of course, you are talking about biomedical applications. You can't have 1 kilogram wireless power transfer system. If you put on patient's chest, the patient may feel really real unease. That's okay for high power applications like electric vehicles and all, but not biomedical applications. And the systems should be very highly efficient. You do not really want heating of human body. And then slightly large transmission distance is needed. Data center is somewhere and patient is moving around the room. So there should be good enough range. Then it should be portable, it should be scalable for variety of medical standards. So these are some of the key features which are required. And lots of efforts are on. Worldwide, we are also contributing a little bit. Say, for example, we are thinking to develop some mechanism for electronic health using WIPT, wireless information and power transfer. We are working really. Some success has come with the use of technologies which are developed for other type of application. And we are trying to modify them for the applications in biomedical electronics. Then with WIPT, you have wireless body area network. They go hand in hand. So WIPT is just one entity of wireless body area network. In wireless body area network, we also need sensors. There are many, many sensors which directly communicate. They don't need charging, but they are transmitting information for healthcare units or even data centers within the hospital or within the building, wherever the patient is. But essentially, WIPT and wireless body area network, WBAN, they are gelled together. So lots of applications are there. We are contributing in on-body sensors. We try to develop, and some of the applications that is actually even the prototype is in our lab. So we have done some sensor. You see, it looks very big, but it's actually the magnified version. It's very tiny. We developed some sensors for wireless body area network. So this is one domain where lots of opportunities exist, even within Kazakhstan, since it's actually a very green country for these sort of applications. Like nothing has happened. So whatever you do, you are bound to be successful if there is some success with your prototype and designs. Then we also contribute in IoT security and trust. The reason, and first question is, why do you want security with your IoT devices? Answers are, you can answer them like, in n number of queries and responses. We do not want to be cloned. We don't want to be impersonated. We want safety mechanism of our devices and data. Since nowadays your financial data, your personal data, they are all on your devices. We don't want to be defrauded. Once somebody gets an idea and inkling of our data, they can just impersonate and misuse. And anything comes to your mind, you can think, okay, oh man, I am being compromised. And cyber stealing is actually a big mafia nowadays. So these things, they are some of, but you can have many questions that can come up to your mind. And in order to address some of them, say for example, even our bank cards, you see, they are all, you see, especially they have RFID within that, and they're not secured really. Anybody can clone that. So a number of things, buzzword you will listen when you are talking about IoT security, hardware Trojan, FPGA based PUF. PUF is physically unclonable function. Then embedded PUF, validation with NIST standards. NIST standards that come from United States, NIST, National Institute of Standard and Technology. So these things, they are all buzzwords, but when you go in, you will find there are many branches and challenges. So we have been trying to develop, and we have contributed some using SRAM based physically unclonable function. And actually, once you do this within computing platform, you also have to develop and validate using FPGA platform. And we have plenty of resources in our lab that even a couple of students are working on that. But this domain really requires good programming skill. And finally, we also work on this domain of RFID and IoT integration. See, RFID is something that has two main components. One is RFID tag, another is reader. Otherwise, if you see a simple inventory and mechanism where you keep on collecting data to see, okay, even in our campus, suppose somebody is coming, they keep maintaining the record of who is coming, like cars and even delivery vehicles, even sometimes ambulances. So they keep doing that. How do they do that? So basically they have some inventory and those management system. So that's one of the engine of that is this RFID platform. And you see, it's all in IoT. Within that, you have this RFID, and RFID has two components. One has tag, another is reader, and reader has some application software. Through that, it keeps sending the data to cloud. That's what it happens. So we have been working a lot for many, many years on this aspect. And this aspect, you see, we do this tag design, and we also do this reader design. This is more zooming in the thing. Eventually, you see, this is how we contribute in this IoT framework. So that was about our work and overall broad circuit system where people having interest can make their career. And we have a lot of resources in our lab. We have Euro practice membership. That is actually, we are the only one in, not only in Central Asia, even in a broader region. Like we are the only university having this Euro practice membership, in our lab has that. And with that, we get this Cadence laboratory that is actually multi-million-dollar software that we get in 500 euros. So, and you see, they provided us this plaque where training future innovators from Kazakhstan. So we have in our lab, so we have these facilities. So what is that Cadence lab or Cadence software? You see, when you design circuits, ICs in your phone, for example, you will see many, if you see this using telescope, lots of connections are there, lots of ICs are there. So they are all analyzed and designed using this Cadence software. And apart from that, Euro Practice membership also gives us the access of free training courses. If those of you who are interested in circuit design and free training courses, you can come to me, you can contact me. I have also one lab engineer, he is an expert, so he will help you with, and they are all free training courses. So I can enroll you in those courses in your free time on weekends. Yeah, they are, and they also give you certifications once you pass them, and they are all free, no money charged. And we also have access to low-cost IC fabrication from Europe and Taiwan. Then we have other EDA tools, electronic design automation tools. We have Keysight Advanced Design System that is again doing the same thing, but it's for more high-frequency circuits. Then we also have CST that also does like more for antenna design and wireless power transfer technique. Even for biomedical application, W-band we can use them. CST. Then we have this Synopsys tools that is also for circuits and systems validation. So we have piled up and we have lots of stuff for software, using software EDA tools, electronic design automation tools. And many students use them. They come to us, we help them, we try to train them depending on their interests. So what exactly they want, then we guide them. Okay, this tool is more appropriate for that applications. And then we have lots of instruments and fabrication facility in our lab. Those of you who are interested, you can visit them as well. At least have a look what these instruments do. So we have this circuit fabrication. It's through our engineering workshop we do. And all these instruments are in our lab, 223 and 222 in C4. We also have this wafer probing system in our lab. We have this system characterization facility in our lab, this antenna measurement facility, and then antenna also for system performance evaluation. This is all 223, 225, 222, 224. So we have lots of instruments and software tools, and our own server is there. So through that, we keep track of our own EDA tools and how its usage as well. And in that, of course, without the help of our key collaborators, it is almost next to impossible to do all this. So we work very closely with Galam and Azhar Saparova in Astana. Then we have collaborators from Canada, Saudi Arabia, Singapore, Japan, China, USA, and some UAE professors are there as well. So we work very closely with them. Some of the students have, after doing their bachelor's, they have moved on to their laboratories for master's and PhD. So that is actually, since now they trust that, okay, these students are working with me. So once they apply, they get additional favors. And finally, for you as a career, if you choose circuits and systems, where will you end up? Study is one thing. So some of the points that I just mentioned, potential career path. Even within this country, you have lots of opportunities for systems engineer in oil and gas sector. If you are expert in circuit systems and sensor networks, you can directly work in oil and gas sector, IT companies, telecom companies. Then you have this aerospace center, Azhar Saparova, and Galam, they really need people with good expertise. Ministry of Defense also, they need lots of people for within this country with expertise in circuits and systems. And mind it, circuits and systems does not just mean circuits. You have to be good in computing domain as well. So that's why you see lots of things you might have seen. It needs lots of coding and those things. So, and since computing without circuit is redundant for circuit system, and circuits without the use of computing environment is like actually redundant in modern world. Then you can also work within the country and outside. Once you go for masters and higher studies, you can find engineering jobs in telecommunication and semiconductor companies. You have wide leading companies like Samsung, Qualcomm, IBM, Intel. you name any. So they are looking for experts, and they really hire readily, and they pay a lot. Since this domain pays you a lot as well. Of course, lots of effort is needed, but it is actually one of the most happening domain in electrical and computer engineering. Then, of course, apart from that, you can have a research career as MS and PhD students at leading institutions around the globe. Our graduates have got admissions in top universities. They are studying there. After education, they have gone out and they are working in those companies. And then you can also have not only engineering jobs in corporate sectors, you can have corporate research careers also. Like they have their own research centers, like especially some of them in Europe, Japan, and United States. They have their own corporate research centers. That's where you can work. And of course, some of them, people, they start their own companies. One of, like 3-4 years ago, one student graduated from here and he moved on to MIT for masters. And then with MIT professors, they started this company called Movandi. They do this Wi-Fi modules, like circuit, the design, with all capable integration, like whatever you can have software and hardware integration, and they work there. So that's it for from me. And I hope that I have a few minutes to respond to your queries. I'm sorry I was late due to misunderstanding.
So yeah, you can write questions.
Yes.
No, I said you can write questions in the chat.
Excuse me, Professor, may I ask something?
Are there any strict requirements for the students who want to participate in my research? Okay. Actually, the only requirement is you should be motivated. So we are here to train students, right? So there is actually no requirement. The only thing that you should bring is your motivation.
Okay, thank you, Professor.
So if you have any questions, if you are shy right now, you can write to me personally on my email, or if you are on campus, you can visit me here in my lab. So you can find me from 9 o'clock until 6, with of course some lunch break and something, but usually you will find me most of the time in this lab. Okay.
Okay, thank you, Professor.
Okay, then okay. Bye-bye.
Thank you, Professor Hashmi.
Yes.
We have a next speaker, Daniel Tosi. Sorry if I read it not correct.
It's okay.
Yeah, okay. Okay. Up next is Daniel Tosi.
Okay. Thank you for the introduction. I think I'm going to be sharing. I hope you can see my screen. Can you?
Yes, yes, we can.
Okay, sounds great. I will just, okay, I just need to minimize, can you excuse me one moment? I just need to minimize the controls, otherwise I'm not going to see anything. Okay, I hope you can hear me. First of all, thanks to everybody for the introduction. I'm Daniele Tosi, and I've been working in NU for the last 7 years. So bringing mainly my my expertise in research for the development of new sensors based on optical technologies, and particularly on optical fiber technologies. So let's go through the presentation. And I just would like to begin from what is more or less the mission of our lab and of our research. As Galileo Galilei, the famous Italian polymath, who is basically the inventor of the experimental method, which leads to experimental science as we are carrying on today. He used to quote, "Measure what is measurable and make measurable what is not so." So I think that all of you are familiar with many sensing technologies that are commercially available or that are part of also of our research that accomplish the goal of measure what is measurable. What we do in our lab is generally the second half of the sentence. We like to make measurable what is not so, because the requirements for the standard or traditional sensors are too strict, because there is not enough sensing point, because there are physical, geometrical or biological limitations to many of the sensing technologies, and therefore we try to bring a technology based on optical fiber that, as a matter of fact, may measurable what is not so. So let's go through it. So fiber optic sensors in general make use of an optical fiber, and I think most of you are familiar with the optical fiber as the technology that is bringing high-speed internet to your home. In fact, we are using exactly the same fibers that are used in telecom networks. So the same fiber that is delivering high-speed internet to your home or through the long-haul backbones around the world is the same fiber that we have in our lab and on which we design sensors. Exactly the same fiber, however, means that the technology has some great advantages. The sensors are small and lightweight. So the thickness of an optical fiber is about 3 times the thickness of your hair, including the protective coating. So one fiber is extremely small and miniature. And nevertheless, it is also biocompatible because it is based on glass. So it's very good for medical devices. It is immune to electromagnetic interference. It can work, for example, in some of the hospital environments where MRI immunity is needed. It allows remote sensing. These fibers are extremely low loss. So it's very common to have the sensing unit placed at several meters, sometimes even kilometers away from the analyzer. And the active region where the sensing phenomenon happens is extremely small. So in general, if you have a little bit of background in electromagnetics, optical fiber sensors make use of optical fiber, which is the most common type of optical waveguide. So the most common way to transport light in a guided geometry. And light travels in the fibers as a wave. And as such, we can have sensors that use all the properties of the wave traveling into the fiber to generate sensors. So waves carry a certain power, and we can actually have intensity-based sensors where the power intensity varies when changes happen on the sensors. Or we can have waves carry a certain spectrum. We can modulate the spectrum using our sensors. They carry also polarization, phase, and in the most advanced sensors, even modes. So the idea is that when the sensing parameter changes, one or more of these properties of the light waves change, and we can detect that with our analyzers. So let's come to the arrangement, the systems of sensors as we know them nowadays. I think most of you are familiar with the single point sensors. Single point sensor basically are sensors that measure one thing in one point, very simply explained. So the sensors can be intrinsic, inscribed inside the optical fiber with a device that you won't see, but that makes the sensing phenomenon happen, or outside of the optical fiber, for example, with the packaging around. This is very common, for example, for pressure sensors that rely on external membranes. And we call them, in this case, extrinsic. So these are common sensors, very similar to other sensing technologies such as MEMS, piezoelectric sensors, electronic sensors, biochemical sensors. These are the sensors as we know them. But in optical fibers, I think we can do more. We can, for example, fabricate multiple sensors within the same fiber and detect the contribution of each of them. This is what we call a multiplexed sensing network. Or we can, for example, use this multiplexing approach to detect multiple parameters within the same fiber. For example, we can have one single fiber that detects strain and temperature. But the key innovation comes when we move on the right side of this slide, when we are going to actually have sensors that are, as we say, distributed. So the idea is that the light already partially reflects when we enter in the fiber due to the scattering events. If we are able to interpret these very tiny reflections, we can detect and localize, and every point of the fiber becomes a sensor. So we can have thousands and thousands and thousands, up to millions of sensors within the same fibers. And we can even have sensors that are semi-distributed, which basically are acting like distributed sensors with detection and localization, but in a very tiny portion of the sensors, often very short and very tiny. So in this case, we have actually the access to advanced properties of the sensors. I was hoping to move on the slides, but that's just, I feel that I have a problem with Zoom, which is a little bit crashing in terms of controls. I apologize, but there seems to be some slight delay. Okay. And I hope I can close the controls and move on. It looks like there is a problem with the I have to apologize one moment, but there is a slight problem between. Okay. Seems like my mouse is kind of not responding. So let's try to. I will stop the screen share for one more. Okay, I think now you can still see my screen, right?
No.
Okay, so let me restart the screen share, and this time I hope it's going to work. Okay, I think now you can see that again.
Yes, yes.
Okay, I apologize. Let's move on. So, as I said, multiplex and distributed sensors enable the detection of physical parameters such as strain and temperature, not only changing in time, but also changing in space and time. So basically, we have access to an extremely powerful sensing technology because it can detect, localize, and detect distributions in space. So we plot this data in maps, which basically report the change of parameters such as strain or temperature over space and time. And signals are sampled in space and time. The time resolution means how fast is our hardware and software to detect the data. But the spatial resolution also means how narrow can be two neighbor sensing point. And we render the map usually in 3D charts where we plot, for example, temperature versus distance and time. But as the data becomes more complicated and we work on planes or sometimes even three-dimensional geometry, the data becomes 4D, 5D, and the sensing system become clearly much more complicated. So let's see the applications, the three main areas where our lab is engaged. The first one is in thermal ablation. Thermal ablation is a novel and minimally invasive approach to cancer care, which makes use of electromagnetic waves sent from a microwave generator, or from a radio frequency generator, or from a laser in general, or ultrasound. That's the principle behind high intensity focused ultrasound, or HIFU. Miniaturized in a miniature applicator to be able to treat a specific type of solid tumors by raising the temperature of cells over 60 degrees. This finds interesting and increasing application in the treatment of some localized type of cancer. For example, lasers are very common in the treatment of thyroid cancer. Microwave ablation and radiofrequency ablation find application in the treatment of liver and pancreas cancer. and laser ablation, for example, in very localized type of cancer, such as brain tumors. So this is an example of how our sensing data can render temperature over space and time. So on the bottom, you have a chart where you have the distance from the tip of the applicator and a time, 0 when the experiments are starting and 1 where we reach the peak of temperature. And as you can see, we render the temperature by estimating how each part of the tissue is exposed to a different temperature variation. So we have the central part of the tissue which reaches very high temperatures, while the temperature tends to decrease on the bottom. Believe it or not, this is done only with one fiber. So one single teeny tiny fiber, and we have enough data to get this type of thermal maps, which estimate the temperature as a function of space and time. But we haven't stopped there. We have been able to evolve our setup by using multiple fibers that have specific type of scattering properties. I'm not going to go too long in that, but they are quite rare type of fibers that are able to create sensing networks. So in a single scan, you're going to detect hundreds of sensors that are displayed on a plane. So the sensor works along the distribution of the fiber, and by having multiple fiber, you can measure the temperature on a plane. For example, in this work, we achieved a total of 96 sensing points over 60 by 15 millimeters, which is a very tiny location. These are the performances of imaging, but they are achieved with a sensor in situ in real time. And this is how the system looks like. This is our interrogator that we are using in the lab. We perform the experiments over a phantom, which basically is a liver meat, which mimics the properties of human liver. And as you can see, the picture shows the small ablation occurring in the tissue. But when we show the thermal maps, you see how precise the data are rendered. So that's basically by extending 4 teeny tiny fibers into a sensing system that has the performance compatible and very close to imaging. They are better even in terms of accuracy. They have very close resolution, for example, to the most advanced MRI magnetic imaging. We're talking about machines that have cost of millions of dollars. And here is a video of how the system is working. So the first chart you will see, as the heating is going in real time, you see the heat propagation. In 25 seconds, the whole ablation has been, and the whole tissue has been heated up. And by analyzing this chart that we can acquire in real time, we can estimate how much of the tissue we have treated to 60 degrees or higher, which is, in this case, the Chan curve here that surrounds the tissue. And we can also measure thermal gradients to study the heat propagation problems. This is a measurement that we have performed in 3 dimensions. So with 12 fibers, we have been able to heat the tissue in 3 different measure in 3 dimensions. So the charts become very complicated, as you can see. We decided to cut some planes to show you the heat propagation, the position of the applicator. This data have been acquired in real time. We post-process the data, but have been acquired in real time. Now look how nicely you have the rendering of temperature with these sensors. We downsample the data just for you to show, but there are more planes. There is basically 1 plane every 2.5 millimeters. So lately, we have also tried to change the properties of the tissue by using nanoparticles and having the so-called nanoparticle mediated ablation. So we have nanoparticles that deposit in the tissue at specific location, and with the specific absorption, they allow to improve the performances. This is our work that we recently reported using a laser ablation setup, where we ablated the tissue using a laser, and we deposited nanoparticle in the tissue and studied how nanoparticles affect the ablation process. Let's go to the next stage of our research. We say that we can do physical sensing, and temperature is one part of physical sensing, but also strain is another part of physical sensing. So what we have been doing is that we have been trying to design shape sensing technologies that using multiple fibers, specifically 4 mounted around a needle, are able to convert the strain into a multidimensional data and reconstruct the shape of the needle in real time. And we have been using that to create a guidance system for epidural anesthesia. This is the scenario in which we operate. So the needle that we have drawn right here is about 8 centimeters long, and is a needle used in epidural anesthesia, same to the ones that is used in clinical procedures. And as you can see, the needle has to be introduced in a space that runs, basically pierces through the skin, passing through the ligament between the vertebrae, and basically reaches the epidural space, which is located right between the L3 and L4 vertebrae behind the ligament flava. So each tissue has different consistency. The needle bends, and we can reconstruct the bending and determine whether the insertion is correct or incorrect. So in the lab, we went from an anatomical model to a phantom that mimics the thickness and the consistency of each parts of the tissue. Then we sensorize the needle using the fiber. This is where our first experiment using a single fiber. And by reconstructing the strain distribution, this time you have the strain color. Basically, each color gives you a different strain data. We can determine whether an insertion has been correct or not by studying the bending. But as I said, we have gone further than that, and we have been able to study the system with 3 or 4 fibers. For example, in this system, our second prototype was using 3 fibers mounted around the needle on an equilateral triangle to determine the bending in each direction. And this is more or less how it works. As needle bends, we can split the contribution to each fiber, measuring the direction of bending. You need at least 3 fibers because we are measuring in a 3-dimensional space. So to reconstruct the strain in 3 dimensions, we need a system of 3 fibers. And we went further with our current prototype that has 4 fibers, left, right, up, and down, which has a much simpler operation, at least in terms of the calculations that we are doing. And by converting the strain into the shape with a trigonometrical model, we can reconstruct the shape in real time. Here is how it works. Here there are 4 videos, basically, that shows the same type of insertion. On the left, a straight insertion. On the right, the needle gets stuck. You will see on the upper screen the zoom view of the needle, where basically we have an exaggerated needle on the other side. And on the bottom part, the real model of the needle, which is very thin. And as you can see in real time, as you can see, I will show it one more time, you are able to view the shapes. Okay, there is some delay in the start of the needle, but I think you can see right now, you can view the shapes of the needle is taking. Notice that despite the very tiny bending, in the bottom part, you have the model in scale. Our system reconstructs the shape in real time. This is one of the most advanced work that we are doing right now and is based on 3D shape sensing. So we talked so far about detecting physical parameters, but what about detecting biological parameters? Can our sensor do that? And the answer is yes. So we design biosensors, and biosensors detect in a selective way analytes that are biological, such as, for example, biomarkers or biomolecules, and in some work, some antibodies even. There have been several methods that have a rapid and repeatable fabrication, and this is one of the aspects that our group is specifically working on. We biofunctionalize the sensors. So we combine the expertise in optics, in the fabrication of the devices, with expertise in biology on how to specifically functionalize the sensor and evaluate that the sensor is effectively detecting. So why using optical fibers? That's because the fibers can have an easy way of fabrication. They can operate in situ and they can operate in vivo. Remember, the fibers are very small. The fibers are biocompatible, and the optical sensors have a limit of detection that is totally unmatched by any other technology. So we can detect concentrations that are ridiculously low. And this is how we functionalize the sensors. We can use aptamers, which are organic bioreceptors, or we can use the famous antibody antigen method, which basically is one of the strongest bindings we have in biology, or even surface assembled monolayers, although we have never explored this part of sensing in our lab. In general, we use either antibody antigen or aptamer-based functionalizations to perform sensing at a higher level. This is one of the advanced work we have done using the same analyzer that we described before, with the same technique using distributed sensing, but using now an etched fiber. So we collapse the outer part of the fiber in order to allow the fiber to be exposed to the outer medium. And with a proper functionalization, we have been able to detect proteins. And as you can see from the performance, we are detecting proteins at in the order of 0.6 micrograms per milliliter changes, which represent more or less proteins below the nanomolar concentrations, which actually is a pretty good result in terms of performance if you consider that the sensor basically has been fabricated without any sensing device almost. We've also fabricated other devices, such as this is an example of the ones that we are currently working on. It's a sphere mounted on the tip of an optical fiber. The fabrication of this sphere is extremely nice. We call them ball resonator, and they can be fabricated in less than 1 minute. So they actually have a pretty nice way to fabricate. And unlike the previous sensors, they are extremely sensitive. They give a sensitivity that is very similar to the most advanced biosensors, despite having a functionalization method that is very similar and very easy. On the left chart, you can see the schematic, but then also the device that we have fabricated with and without a gold coating, which allows to have better immobilization of bioreceptors. And with these sensors, we have detected at concentration also of 0.4 picomolar, which are very low. And I want to anticipate that by even improving the sensors, we have done some devices lately that do also this improvement. This is a very recent result in our lab. We have been able to detect concentrations that are in the order of about 100 aptomolar. So 100 aptomolar is an extremely low concentration, okay? We're talking about concentrations that are in the order of 10 to the minus 16 molar. If you remember from your chemistry courses, you are used to make reactions where you take 0.2 mole of these together with other 0.5 molar of these. We are detecting at 10 to the minus 16 molar concentration, which is a very low limit of detection. So I want to conclude here my talk. In general, we have applied basically optical fiber sensing in 3 main key areas: thermotherapies, shape and strain sensing, and biosensors. Although, of course, we are trying also to explore other areas. There is a strong impact of fiber performance and fabrication methods on the devices, and we are currently and constantly try to push the performance in terms of spatial resolution, limit of detection, accuracy, always to the next level. We have a pretty much of a lab suited to host experimental research on advanced sensors. And as I said, our ultimate mission is make measurable what is not measurable, make measurable what is not so. And I just would like to thank some of the partners that have contributed to our research all around the world, including in the United States, in Italy, in France, in Portugal, Spain, in China, and in Russia. We have been able to build a very strong collaboration networks with many groups who have also exchanged devices and researchers with our group. So I would like to thank you for the attention. I hope the talk was interesting, and I, of course, am open for questions.
Thank you, Professor Daniel. You can write your questions in the chat or turn on your mic and ask them.
please feel free to ask.
Excuse me, Professor.
Yes.
Is this the only research that you conduct? I mean.
Well, only that's a big job.
No, like, excuse me, please, but in comparison with other speakers that will today, also like, there are probably some multiple branches at least in your research. Like,
well, that's I understand the research in optical fiber sensors is quite specific, but when actually come to building the devices, there is a lot of hard work in making devices that have extremely high performance. This is not a sensitive technology that is very common, but when it works at extreme performance. Okay, and there is not many groups around the world that apply this concept in small scale to medical devices. In general, these concepts are applied for longer scale, for example, sensing over hundreds of kilometers, in geotechnical structures, in dams, in the oil and gas, in the bridges, for these type of applications. That's what these sensors were originally meant for. We are targeting instead medical devices. We are trying to make everything smaller, everything that fits into the next generation surgical and medical devices. And that requires skills that range from engineering to biology. So it's not a very simple job, okay? But doable.
Yeah, I see. Thank you, Professor.
Okay. I see one question in chat. Are there specific requirements for students to join the research group? That's a good question. In general, we expect students to be, working. Depending on, of course, the seniority level, you might or might not have, some of the background. In general, we provide training. It's, to everybody. So the idea is that you won't be able, to start immediately. First, there is a little bit of training step, and then you can work on your own projects. So no, there is no specific requirement. Obviously, you need to be motivated because the research is hard. We go through several failures. We try to develop things that other people are not doing. So there is many failures involved. Motivation should be always high. Otherwise, people tend to give up after things don't work 1 or 2 or 3 times. And that's very common. Okay, some of the devices that you've seen here that represented also our best result that we published on high impact journals. Some of the devices, sometimes we made it the first or the second times. Sometimes we made it after the 25th times. Actually, in one case, we made it in the 27th times. So yeah, it needs commitment, obviously, discipline, motivation, soft skills that are extremely important. Hard skills in general, it would be nice for the students having a little bit of background in electromagnetics, but we can supply with that. There is a training you can make, and to just get going. So we have worked with students that are also in 3rd year undergraduate, but also we have postdocs in the lab. So our group has about 15, 16 people right now.
Thank you very much, Professor Daniel. I think
Thanks to all. Thanks to all. I will stop the screen share now. And thanks for the chance to have this discussion. I think I will pass to the next speaker.
Yeah, okay. So next speaker is Professor Ikechi. Professor Ikechi, are you here?
Yeah, I'm here.
I'm sorry for the delay. There was a confusion with misunderstanding of the schedule by some professors. So are you ready?
I'm ready. Something is wrong with my camera. Yeah, it's failing to start. Okay, let me try to share my screen. Okay. I hope you can all see my screen, right?
Yes.
Yeah, sorry for the lack of video. So first of all, I would like to thank the organizers of this event. This is a very good initiative, and I would say well done. It's a good job. So my presentation today is mostly about what I do in my laboratory. So as you can see in the title here, it revolves around integrated device solutions, photonic computing, and nanophotonic systems. So the name of my lab is Integrated Device Solutions and Nanophotonics Laboratory. Okay, so basically, I have divided my area of research into 4 parts. And I believe most of you or some of you here are already conversant with my research group or what I do, but I'll still go through it. My presentation is gonna be a very short one so that, yeah, you guys could have a rest from today's talks. Okay, so the first part of my research is in communications infrastructure, where I had it divided into 2 parts, the optical part and the wireless infrastructure part. Then we have the signal and power integrity, digital photonics, photonic computing, and silicon photonics. Now, for the part of optical link infrastructure, so the focus is mostly on short-range interconnects, optical interconnects. So basically, if you look at your motherboard, for example, you have a lot of chips there, CPU, your memory, and a lot of other components there. And if you check, you can see that they are all connected together using some kind of copper links, right? So basically, as operating frequency of these processors increases, we start to have issues in the electrical lines. So we have a lot of issues such as crosstalk, and we have electromagnetic interference, and a lot of other issues. But then there is a solution to these issues, and that the solution is trying to replace these electrical links with optical fiber or optics. So basically, why are we doing this? Why optics? Because optics offers, it has immunity to electromagnetic interference, immunity to crosstalk, and a lot of other advantages, as well as low power consumption. So basically, the solutions offered here, we have the optical chip-to-chip interconnects, CPU to memory interconnects, and so on. So basically, if you are trying to introduce optical link in the motherboard of a CPU, sorry, of a computer, for example, you don't just lay the fibers or the waveguides in the motherboard, because the signals coming out of the CPU going to the memory and vice versa and so on, they are in electrical domain. So we need to find a way to convert it from electrical to optical and vice versa. So because of this, we need to develop some kind of transceiver. So when I say transceiver, that is a transmitter module and a receiver module. So a transmitter and receiver module together is called a transceiver module. Now, we previously, we have worked on the design of these transceiver modules. Now, if you look at the picture we can see here, this is CPU to memory optical interconnect, right? So on one side, we have the transmitter module, and on the other side, we have the receiver module. So basically what they do is to convert electrical signals from the CPU to optics, and then at the receiver end, convert it back to electrical signals and then send to the memory, so on. So a module consists of a driver IC and a VCSEL, right? So VCSEL, this is laser diode. And then at the receiver end, the receiver module is you have the receiver IC as integrated circuits and the photodiode. So basically, the signals gets converted here to optics, goes to the embedded optical fiber layer, then to the other end of the chip. So this is part of what we do in my laboratory. We have done this previously. So now, still part of the optical link infrastructure, we have what we call the active optical cables. So in the previous slide, I have mentioned about the optical PCBs and so on. So basically, we have companies that are leading in this. One of them is IBM, has been working on this. So back in the day, we had some projects together with IBM where we helped to develop these optical PCBs. So now we're looking at active optical cables for data centers. So we know about data centers, that hosts, a lot of data and so on. And data centers have to be able to transmit data at very high speed. So basically, you have what we use optics to interconnect all these data centers, the computers, the hard drives, and so on. So these connections are made by, thanks to these active optical cables. So this active optical cables is just contains transceiver modules at both ends. So we have worked on this previously. So here we have a transceiver IC and the packaging. So we designed the board, we designed the ICs on it and the modules in it, so that you can, at one end, it can, convert to electrical to optical and vice versa at both sides, at both ends. So basically, this is one application of the transceiver modules in active optical cables that are used in data centers and also for the telecom industry. Now, looking at the wireless infrastructure. So we have, we all know that you can transmit data. We know about microwave communications and free space optics. So in free space optics, that's where you can transmit data from one point to the other. So free space optics is a very cheap way to deploy communication, but the only drawback is because it works on point-to-point connection, which means if anything comes in between them, it will disrupt communication from one point to the other. So this is another application of the wireless infrastructure. And then when it comes to the microwave or RF case, so we know about our mobile phones, your laptops, has a lot of technologies. You have a Bluetooth, your GPS on your LAN. So all these things are enabled by what we call the wireless communication front end. So which has your transceiver. In this case, we're looking at the RF or microwave signals. So what we do in our lab, we don't work on antenna. No, we only work on just some specific components here, which is the low noise amplifier and the power amplifier design. This is all we do when it comes to the electronics for free space, for wireless infrastructure. Now, we look at photonic computing. Here, we know that the frequencies of our CPUs, you have your CPUs that had your 4-core, your 8 cores, and so on, that improve the performance of your current computers. But then over the years, we have seen that the processing speed has increased over the years, but the problem is that the memory speed has not increased at the same rate. So we are trying to see a way to bridge this gap, and one solution is to bring in optics. So basically, we are looking at improving optical memory access solutions, developing these solutions for easy access to the memory and vice versa. So we have tried to develop some, we are currently working on designing some optical memories. But in our laboratory, we have been able to design some silicon photonic logic gates. We have designed other logic gates. So we have developed logic gates that work up to 1 gigabits per second. That is for passive gates based on passive resonators. But we are aiming to reach up to 40 or 50 gigabits per second of transmission rate or data rate. Now, what is the feature of computing? So, there are two different directions. A lot of people go with quantum computing and some go with photonic computing. So in my area, we are moving towards photonic computing, and it is built. So we are trying to find a way to bring in the electronic components and optical components together on one single chip to improve the performance of the total of the computer itself. So there have been a lot of works on optical fast Fourier transforms, and of course, quantum photonic processor. But still there's doing an intensive research in this area. Okay, so what are the applications of what I do in my laboratory? Is very broad. You have consumer electronics, IoT, high-speed computing, you have AI, unmanned aerial vehicles, you have your image sensors and so on. So I have a couple of projects that are ongoing. We have a memory, 40 gigabits per second memory access solutions for the next generation computing systems. So these are an ongoing project started this year for 3 years. So if you're interested, please contact me. We have another project. This one is energy harvesting units designed for peroxide solar cells. And the application is for IoT devices. So this is already also another ongoing project. And also we are also designing energy harvesting units for building integrated photovoltaics. So this is also going to be getting the energy harvesting energy from peroxide solar cells. So this is also another project. So this one is an MES project. So it is ongoing. So we have a couple of other projects going on, and we have a lot of partners. We are working with University in Nanjing. We are working with KAIST. And so basically, if you join my research group, you have chance for internships to any of these places, to China, to Korea. So we also have a planned project, which is development of AI integrated linear frequency modulated photonic radar for autonomous vehicles. So this is a planned project that we plan to do in the future. So basically, this is the end of my presentation. If you have any questions, let me know. Yeah, currently we are all online at the moment, so you can easily send me an email if you have any questions, or you can visit my website to learn more about my labs. But I'm ready to take any questions if you guys have any. Any questions?
I have a question. You thought you had internships. So which year of study are you looking for?
So basically, for you to qualify for the internship, first of all, you need to be doing research, right? So internships is recommended for year 3. So basically, let's assume that you start doing research from your second year, which means by the 3rd year you qualify for internship. And if you start from the 3rd year, then at least you must have worked for at least 2 semesters for you to qualify for internship. So because the internship is all about, how do you call it, is still part of the research. So when you go to those collaborators university, you are going there to coordinate our research over there because we are working together on the same project. So whatever you're going to do there is still going to be part of the project. So that's the whole idea of the internship. So it's not an internship to go there and then do something else. No, it's still going to be part of the project.
Okay, thank you.
Mm-hmm. Any other questions? Okay, all right. So anyway, if you don't have questions now, you can feel free to send by email later. So I think I'll stop sharing my screen now.
Okay, thank you very much, Professor.
Okay. All right, thank you for having me.
Also, thanks everyone who attended this session and sit through the end. I guess it's the end of the meeting. So goodbye.